Good day. My name is Julian Page Ang, and I'll be discussing about the kinds of graph coloring. So first, what are graphs? They contain vertices and edges. Below are some examples of the kinds of graphs, which are planar, simple, and connected graphs. A planar graph is drawn on a plane without any overlapping edges, while a simple graph has no vertex adjacent to itself and has no more than one edge between any two vertices. On the other hand, a connected graph can end and start at any vertices. Additionally, a clique is a subgraph of a graph. So what led to the idea of graph coloring? One of it was the four-color theorem proposed in the 19th century to solve a map coloring problem, which was said to be the most popular graph coloring problem. It was a problem questioned by Francis Guthrie, whose brother requested it to be proven by Augustus De Morgan, a professor of mathematics at the University College London. It basically states that any map can be colored using only four colors. However, this has proven to be applicable only to planar graphs, as planar graphs are formed when edges connect two adjacent vertices representing the regions of a map. Subsequently, it became the first ever theorem proven using a computer in 1976 by Appel and Wolfgang Haken. The other problem that led to the idea of graph coloring was the Königsberg Bridge problem, which questions the possibility of crossing each of the 7 bridges of the town Königsberg exactly once. Graph coloring basically involves coloring parts of a graph under certain conditions. The chromatic number represents the minimum number of colors used, while an independent set includes parts of a graph that are not adjacent to each other. The maximum size of an independent set is the maximum number of colors in a graph. However, it is considered as an NP problem, since no polynomial time algorithm can possibly be formed for computing the chromatic number of a graph coloring problem. There are 3 types of graph coloring. These are the vertex coloring, edge coloring, and face coloring. First is the most common graph coloring problem, which is vertex coloring. It involves coloring all the vertices of a graph on the condition that adjacent vertices must not have the same color. Adjacent vertices are essentially two vertices that are connected by an edge. One example that applies vertex coloring is in Sudoku, wherein each cell would represent a vertex and the vertices in the same row, column, or block would then be connected by edges. Another application would be in mobile radio frequency assignment, where the vertices would act as the towers and the edges would connect the vertices that are in similar locations or in close proximity. On the other hand, edge coloring involves coloring the edges of a graph without coloring the adjacent edges with the same color. Adjacent edges are essentially edges attached to the same vertex as their endpoint. This best applies to job fairs, where a person would usually have some interviews with people from different companies. Vertices would then represent the companies and the people job hunting, while edges would be drawn between a person and the company that the person wants to be interviewed. The lowest number of time slots needed, so that everyone would have the chance to be interviewed by every company they want, can then be determined through the edge chromatic number, which represents the different time slots. Lastly, in face coloring, faces of a graph, which are regions on the graph enclosed by edges, sharing an edge must be colored differently, while faces sharing a vertex can have the same color. An example would be in map coloring, where colors are assigned to different regions of a map, such that regions sharing an edge are colored differently, while allowing those sharing a vertex to have the same color, similar to what was applied to the one in the four-color theorem. As shown from the slide, it is a sample problem related to making fish tanks. This involves the application of vertex coloring on the condition that the minimum chromatic number must be determined. The minimum chromatic number will then represent the number of fish tanks needed. As shown in Figure 1, each type of fishes are first arranged separately in different tanks. Moreover, since one must usually check the compatibility of the fishes before grouping them together in the same fish tank, their compatibilities are then checked through Figure 2, wherein the intersection between species that are incompatible are shaded red. By knowing their incompatibilities, the diagram presented in Figure 3 is formed, where each type of fish is represented by vertices, while the edges serve as a connection between the types that are incompatible. Since goldfish and koi are not adjacent, they are both colored yellow. On the other hand, all other species of fishes that are adjacent to them but are not adjacent to one another are colored gray. This results to a chromatic number of 2, which represents the minimum number of tanks needed. Furthermore, two independent sets can be derived from the diagram, one of which is a set that contains the species of goldfish and koi, and another set that contains the other species of fishes, which includes the barbs, angelfishes, rasboras, danios, corycats, and gouramis. The previous sample problem is an example of a bipartite graph, which is a graph whose edges are connected to different vertices, forming two independent sets of vertices with each set colored using only one color, resulting in a chromatic number of 2. Furthermore, according to the Koenig-Egevary theorem, the matching number, or the maximum independent edge set, which is a set of edges that does not share the same endpoint vertices, and the vertex cover number, or the minimum vertex cover, which is the lowest number of edges connected to a vertex, are equal in a bipartite graph.